Another thing we need to work with when we are working with speakers is the speaker impedance compared to the amplifier output impedance. The speaker impedance is a result of the resistance, the capacitive reactance, and the inductive reactance of the speaker. And the speaker is pushing air, and that's going to put some back force on the speaker. And so, like a motor, if you put a voltage across the motor, that motor is going to turn. As that motor turns, it acts like a generator and pushes back on the voltage that's coming in. And we get an equilibrium. But if you put a load on that motor, like you're turning a screw with an electric screwdriver, or you just clamp it with your hand to slow it down, it's going to produce less of that back EMF and more current is going to flow through it, facilitating the current needed to make it work harder to work against that load. Same thing happens with the speaker. It's pushing against air. So if there were no air to push against, the impedance would be one thing, because as the alternating current hits the speaker, it's going to vibrate. It's going to then produce its own current, which pushes back. But if it's pushing air, that's going to cause it to move slower, and it's going to have less of that back EMF, and therefore more current will flow through it to facilitate it moving that air that it has to work against. And so that's going to actually lower the impedance. But that's not really important, because the speakers are simply rated at a certain impedance, typically 2, 4, 8, or 16 ohms. Do they have 32 ohm speakers? Haven't seen one, but I wouldn't be surprised if I saw one. But those are your typical 2, 4, 8 is the most common, and maybe 16 ohms. But again, with speakers, what we are trying to do is we are trying to move air. We are trying to produce mechanical motion. And remember that power is the production of heat, electromagnetic radiation, or mechanical motion. And so we want to produce power in those speakers to move that air. So what we want to do is get the best impedance match to produce the most power in the speaker. So let's take a quick look at how that works. I do have a video and some reading material on impedance matching, and where I go into details explaining this, but I'll just give a quick overview. Let's look at this as direct current. So we'll just say we have plus 10 volts here, and it'll give the same results with direct current as alternating current. And we'll just use resistors for our impedances. There's one impedance, there's the other impedance going to a ground or a common connection. And this impedance represents our amplifier's output impedance, and this impedance represents our speaker load impedance. So let's take a look at this DC circuit. And let's say that our amplifier has an output impedance of 4 ohms, and that's not going to change. Let's see what happens when we put different impedances here. Let's start by just making this a 1 ohm impedance, just for the easy math. So what do we have? We have a total of 5 ohms of impedance, and that 5 ohms of impedance is across 10 volts. So we're going to get a current of 2 amps. So 5 ohms into 10 volts gives us 2 amps. Let's see how much power we have at each of these impedances here. We have a total of 10 volts to work with, and the total voltage across our 2 impedances must add up to 10 volts. Basically 2 amps going through 1 ohm is going to give us 2 volts, and then 2 amps across 4 ohms is going to give us 8 volts. So there's our voltages. 8 plus 2 equals 10. So far, so good. What is the power? I'll write the power over here. So I have 2 volts, 2 amps. So power is equal to voltage times current, or E times I. So 2 volts times 2 amps gives us 4 watts in the load. How much do we have here? Well, we have 8 volts and 2 amps. That's going to give us 16 watts. So in this case, we have 4 times as much power in the output impedance as we do in the load impedance. We're not efficiently moving that power. So let's just write that down here to remind us. Our output power was 16 watts, and our load power was 4 watts. We'll just remember that there. So in this scenario, we're only developing 4 watts across our speaker. So what can we do? Well, let's see what happens if we increase the impedance of the speaker. Well, we increase the power. Well, let's find out. So we'll increase that to all the way up to 16 ohms. That'll be a good dramatic increase. What happens to our current and our voltages here? Okay, at 16 ohms, We have 16 ohms and 4 ohms. That's a total of 20 ohms. So 20 ohms goes into 10 volts is going to give us 0.5 amps. So we're going to end up with 8 volts across our load and 2 volts across the amplifier. So how much power are we going to produce? We should have erased this. Let's just go ahead and erase that now. How much power are we going to produce? In the load we have half an amp and 8 volts. 0.5 times 8 is going to be, again, 4 watts. So I'll just write that there. We're still at 4 watts. What's happening up here? Well, we have half an amp and 2 volts, so 0.5 times 2, that's 1 watt up here. So we're not producing an incredible amount of power up here, but we're still only producing 4 watts here. So that's our scenario there. Now let's make these impedances equal. Let's get rid of that and all of the other numbers because they're all going to change. Once again, this is remaining at the same impedance to show how the load impedance is going to affect the power as we change it compared to a stationary output impedance. And we're going to make that 4 ohms. Now what do we have? Well, we have a total of 8 ohms of impedance. How much current are we going to have? Well, we have a total of 8 ohms goes into 10 volts. That's going to be 1.25 amps. And how much voltage are we going to get? Well, we know that in a series circuit, if we have equal resistors, we will have equal voltage. So we're going to have 5 volts here and 5 volts there. 5 plus 5 adds up to 10. And that will go right here, 5 volts and 5 volts. So let's take a look at our power now. So we have 1.25 amps times 5 volts. That gives us 6.25 watts. And 1.25 amps across 5 volts, well, it's going to be the same, 6.25 watts. So now with the impedances matched, with the output impedance matching the load impedance, we get the same power across each one. It looks a little inefficient because we'd like to get less power here and more power there. But notice that when we increased this above 4 ohms, our power across here actually went down. So there's going to be a peak. At this scenario, we're going to have a certain amount of power. At this scenario, we're going to have another amount of power. It looks like the same power, and it's going to go and do that, peaking at 6.25 watts. And when we have 4 watts here and 4 watts there. So the maximum we're going to get is 6.25 watts, and that is with the impedances matched. Even more importantly, not only are we going to be less efficient in moving that air if they don't match, look what happens if this impedance is too low. We're going to transfer our power up to here instead. So here with the impedances matched, we have 6 watts. That's what it's designed for. But if this impedance is 1 ohm, we're going to go all the way up to 16 watts here. And that's not designed for that much power. It's going to be dissipating too much heat because here we're going to convert our power into motion. Here we're going to convert our power into heat, and that'll probably damage the amplifier. Here we're going to convert the power into motion. The only heat we'll produce here is from whatever resistance is in the wire, which is not much. But here all we have is resistance, and so all of our power is going to be converted into heat, and that's probably going to burn up the amplifier. So be very careful about putting too low of an impedance on the output compared to too high. Going too high, we're just going to lose efficiency, but going too low, we can actually damage the amplifier. So our speakers are going to be rated at a certain impedance, and your typical speaker impedance is going to be 8 ohms. So I'll draw a speaker here. That's an 8 ohm speaker. And your typical output of your amplifier is going to be, guess what? 8 ohms. And that's probably what you're going to see most often. The impedance of the wires here is inconsequential because at these frequencies, the impedance is much, much lower than the resistance, and this is very low resistance, so they don't even really figure into the equation like the feed line of radio where we have a different situation we'll talk about down the road. So we don't care about the impedance of the wires. That's going to be very, very low and inconsequential. But we want our 8 ohm output to go to 8 ohm speakers, and that's what our most typical situation is going to be. But we might find systems such as public address systems where we have different choices. And so if you have a public address amplifier, you don't simply have a speaker output, but you have multiple outputs. And you might have outputs for different impedances. So you might see something like, here's a common connection, and then you have several connections for something like, let's say 2 ohms, 4 ohms, 8 ohms, 16 ohms, and let's say 70 volts. So with 2 ohms, 4 ohms, 8 ohms, 16 ohms, 70 volts, what the heck is that? I'll talk about that when we talk about PA systems in another video. But in this case, we can talk about it because we can figure out what can we do. If we have a 2 ohm output, so we're coming from the common, and the 2 ohm, what does that mean about our speakers? We need to have a combination of speakers that gives us 2 ohms. You can buy raw speakers that have impedances of 4 to 16 ohms. So let's say we have 2 4 ohm speakers. I'll put one here and one here in parallel. So these are 4 ohm speakers. 2 4 ohm speakers in parallel will give us what impedance? Remember, if your impedances are in parallel, if they're equal, the total impedance is half of either one. So together that's going to be 2 ohms. So that 2 ohm output would be for some combination of speakers that gives us 2 ohms, which this would give us. And of course the 4 ohm output could go to that 4 ohm speaker. So let's move that over to here. So there's our 4 ohm output going to a 4 ohm speaker, or maybe it goes to 2 8 ohm speakers. Quick drawing of 2 8 ohm speakers here. So 2 8 ohm speakers in parallel is 4 ohms. So that would work there. What about the 8 ohms? Well, that would just go to some combination of speakers that is 8 ohms. Would that be a single 8 ohm speaker? Could be. Could that be 2 16 ohm speakers in parallel? Yeah, it could be. Could that be 2 4 ohm speakers in series? It could be. How about 4 8 ohm speakers? I'll leave this like that. So those together are 4 ohms. What if I put that in series with 2 more 8 ohm speakers that are themselves, let's see if I can get this right. There goes to the common. There's the other speaker. Do I have this wiring right? 8 ohms. Okay, 2 8 ohm speakers in parallel, that's 4 ohms. 2 8 ohm speakers in parallel, that's not 42, that's 4 ohms. And so together in series, that's 8 ohms. So you might wire all kinds of different combinations of speakers to match the outputs here. But I'm going to go ahead and talk about this right now because I've gone this far. Might as well talk about that. What's that about? That is for systems where you don't know what speakers you're going to have, or you want to work with the same speakers in every place. We have a system where the amplifier now acts more like a regulated power supply. Remember, the regulated power supply, if I just draw the model of that, there's the output impedance of the power supply, there's the load impedance. And remember, this acts like a variable resistor, so that as this load impedance goes down, the voltage across it is going to go down. And so this impedance is going to go down to match to bring that voltage back up. Watch my videos and read the material on power supplies to fully understand that. But basically, the impedance of the amplifier now is going to change to keep this voltage constant. Well, this is not a constant voltage situation because we're going to have loud sounds and quiet sounds. So if we have a 70 volt system, that means that at the highest possible volume, so there's our volume limits there of our sine wave, we want this voltage to peak at about 140 volts because we want the RMS voltage to equal 70 volts. So 1.414 times 70 is going to be approximately 140. So that's going to peak at 140 volts, but have an RMS voltage of 70 volts at the peak volume. So that's what a 70 volt system is. It's going to adjust its output impedance to make sure that when it's producing its loudest output, that is going to produce a 70 volt RMS signal if it's a sine wave. So all we need to know though is that we need to set up the speakers for that 70 volt system. So how does that work? Well, in that case, the speakers have transformers. You might buy speakers with a riveted on transformer with several taps on it, or you might buy raw speakers and then have a transformer that goes between it and the amplifier. Let's assume that we have a transformer. Here's our transformer, and we have some outputs here and some inputs there. And here's our amplifier, which is 2 wires, our common, and our 70 volt output. And what we're going to have here is an output for different impedances or different powers of speakers. So the speakers for a PA system will be rated either as impedance, like a normal speaker, or they might be rated as power. So we have several possibilities here, a common, of course, and we will have an output for like 8 ohms, 16 ohms, 4 ohms, and then we'll have some more outputs, need a little more room here, for like 1 watt, 5 watts, 10 watts. I don't know the numbers off the top of my head. I think they're like 1 watt, 2.5 watts, 5 watts, and you'll have something to match the wattage of your speaker. So your speaker will be rated in either ohms or watts, and you hook it up to the proper output of the transformer right here. And the input, you're going to have a common, and you're going to have inputs for either, once again, different impedances or different voltages. So you might have 100 volts, 70 volts, I think those are the 2 common ones, and maybe 16 ohms, 8 ohms, and 4 ohms, or whatever. And so that matching transformer matches your speaker over here to your amplifier over here. Just have to hook it up to the proper connections on that transformer. And a lot of speakers for PA systems have that transformer riveted to the case with its different outputs. Of course, it'd be oriented a little differently, and so you don't worry about the speaker, just the connections on the other side of the transformer, because that speaker is made to match that particular transformer. So what does that do? Well, if we are using a 70 volt or 100 volt system, what that means is that we can put all the speakers we want in parallel, and the amplifier will compensate. So we have a speaker here, and it's a 70 volt speaker, so it's wired either through its own transformer or through another transformer, so that is for a 70 volt system. So here comes our common, here's our 70 volts, and we can just tie that speaker to the common and the 70 volt input, and we need another speaker. Once again, it's a 70 volt speaker, and that's going to connect in parallel, and the amplifier will simply compensate for the change in impedance. Of course, the impedance is going to be half of what it was before, so the amplifier will change its impedance. It'll actually lower its impedance to make sure that we keep that constant voltage at the highest output. And I can do that ad infinitum to have all the speakers in parallel that I want for the PA system. So that is dealing with speaker impedance and with speaker voltage in PA systems. Now, in my video on speaker arrangements, I'm going to talk about a special case of a PA system where we actually want to take the polarity of each speaker and flip that. So basically we have, in this case, our common and our 70 volts. Here we want to run the 70 volts to the common and the common to the 70 volt input. And it's just input of a transformer, so there's no real polarity there other than what it does to the phasing of the speaker. And I'll show a special case where we want to flip those in the PA system, but we'll talk about that when we talk about speaker arrangements in another video.